Stanley here. Let's talk about limits at infinity. We will explore limits at infinity in order to differentiate between the two conditions. Recall from pre-calculus lessons related to analyzing the end behavior of functions. In the exercise below, use this prior knowledge to find each limit at infinity. You also learned about end behavior in Algebra 2, so this might feel like really long time ago. Very early in pre-calculus, you talk about functions and their graphs. And also you talk about it in Algebra 2. So, refreshing our memory. If we have this polynomial function here, this is a quartic, because think about what would it be if we actually multiplied it out. We would have x squared times x squared. So this is quartic. It would have a degree of 4. And it is a polynomial, which we've already learned that polynomials are defined over their domain. They're continuous. And then you might remember in the end behavior model, like when we're looking at end behavior, what happens to the graph? The end behavior is that if the leading coefficient is positive and the highest degree is even, that tells us what happens to the graph. And so that's the information that we're using. If you need to review that, let me know and I can send you some materials, or you can just look it up. So again, the leading coefficient is positive. Because remember, it would be x squared times x squared, so it's just 1x to the 4th. So that's a positive. Leading coefficient is, let's say this. Leading coefficient, oh, that was supposed to be my eraser. Sorry, I'll make it a shorter way to say it. I'm messing us up now, even though it was supposed to be faster. We can say A is greater than 0. That means it's positive. Now, if you're not remembering what is A, remember all that stuff, then go ahead and write it out. A is the leading coefficient so that you can refer back to it later. So based on this, the leading coefficient is positive and the degree is even. We know that as x approaches infinity, f of x increases. The graph is increasing without bound. What does that tell us? It's going where? It's going to positive infinity, right? So the limit equals infinity. That's our answer. Let's write it up there at the top instead of down at the bottom. Let's look at the next one. Similar, try to do it and then unpause the video, but notice that this one is a positive leading coefficient, but it is an odd degree. So we've got a cubic function, cubic polynomial, cubic function, either way you want to say it. We still have A is greater than 0. The leading coefficient is positive. And what happens to the cubic? Remember, if you think about the graph of a cubic function, it's like a, kind of like this, right? Notice right here, I should have pointed this out on the other one. This one is x going to negative infinity. Over here, we were going to positive infinity. So that's why we said as x goes to infinity. On this one, what can we say? As x goes to negative infinity, what happens to our cubic? It's coming down here, right? Because when we do 5 times whatever cubed, if that's an x is negative, we're going to get a negative, and that 5 is going to change, right? So that's why it's going to go down. So as x approaches negative infinity, f of x decreases without, I'll write it out for you, without bound. So that means the limit is what? The limit is negative infinity. Okay, if you haven't paused to try one yet, you can go ahead, but this one is a little bit different, so it might not help. Here we go. This one, remember we talked about comparing the top and bottom. This is a rational function, and so we've got x squared on top and x squared on bottom. There is information to review how to find vertical, horizontal asymptotes. So if you need that information, just let me know. So, but here, what do we notice? The top and bottom have the same degree. They're both x squared. So what we can do is actually just look at the leading, the highest degree on top and bottom. So we'd have 3x squared over x squared. And what happens? The x squareds cancel out and we're left with just 3. So this has a horizontal asymptote. horizontal asymptote at y equals 3. So this is what we know. As x, again, we're approaching positive infinity. As x approaches positive infinity, f of x is approaching 3 because that's a horizontal asymptote. Okay, so y equals 3 is horizontal asymptote. We technically wrote that twice, but that's okay. So let's look at the next one. Can we use the same rules? We can, but what happens in this case, they don't have the same degree. We have 5x over x squared. When we reduce that, we get 5 over x. What does that tell us? The denominator has a higher degree. Than the numerator, right? So y equals 0 is a horizontal asymptote. Because what's going to happen if we have a constant 5 divided by x, as x gets bigger and bigger and bigger, what's going to happen to 5 divided by a bigger and bigger value of x? It's going to get closer and closer to 0, but it's never going to be exactly 0. So in this case, as x approaches negative infinity, y approaches 0. Okay, so our limit is 0. So let me move my writing over a bit to write that. So the limit equals 0. Okay, so let's go to the next page now. This is just sort of a summary for us. There are only 4 possible outcomes when you explore behavior to the extreme right or left. So as x is increasing to the positive infinity or the negative infinity, there's only 4 possibilities. The curve can increase without bound. So look here, we've got x is going this way to positive infinity. What's happening to our graph? It's going up to positive infinity, right? On the next one, b, x is approaching negative infinity. So as x goes this way, what's my graph doing? It's going down. It's approaching negative infinity. C, the curve can become asymptomatic to the x-axis. So our x-axis is here. And notice our 2 graphs are going near to it, but they're never going to cross it. So that's a limit of 0. Let me write that a little better. That's a limit of 0. And then the last opportunity, the curve can become asymptomatic to a specific value. So here you can tell there's a horizontal asymptote here at positive 3. So in this case, that graph is going to 3 as it goes to negative. Notice it's going to negative infinity. It would actually be the same in both cases. One would be positive. I mean, they're both going to 3. Sorry, positive infinity or negative. But it is important for us to pay attention to what they actually asked us. Even back here on C, we really only needed to look at the positive. X approaches positive infinity, but you can see when it's got that asymptote, it's kind of the same on both sides. Okay, revisiting the rules for finding potential horizontal asymptotes for rational functions from pre-calculus. So if you were not following these rules, you couldn't remember, this is a very important box for you to make yourself a note to remember these rules. Okay, so you might highlight this. If the degree of the numerator is less than the degree of, let's make it a highlighter. The numerator, that wasn't supposed to be a pen, sorry. The numerator is less than the denominator, then the limit is 0. If the numerator equals the degree of the denominator, the degree of the numerator equals the degree of the denominator, then what happens? You get a coefficient. The coefficient of the numerator's highest power over the coefficient of the denominator's highest power. We had that one example where it became 3. Sometimes it'll still be a fraction. If the degree of a numerator is greater than the degree of the denominator, then the limit does not exist. Okay? Because it's going to continue to go higher and higher because the top value is getting bigger. And so it's getting bigger each time. So topic 1.9, connecting multiple representations of limits. We've done this a little bit, and this is a good opportunity to do it again. Example number 6, divide every term in the rational expression by the highest power of x that appears in the denominator. Then apply the properties of limits to evaluate each piece to find the limit at infinity in behavior. Okay, so during pre-calculus, I know we did what they're talking about here, divide every term in the rational expression by the highest power of x that appears in the denominator. You may not recall it, but when we were trying to find important points and asymptotes and all that, we did do this. But let's look at what they mean. The highest degree in the denominator is x squared, okay? It's the highest power of x. So what we're going to do is write this whole thing out. I will write it out for now, but you don't have to actually. So it's basically, this is what we're doing. We're dividing every one of these by x squared. Now keep in mind, like I said, you do not have to write that part down. I just wanted you to see it for this one time. But now this is what you would write. 2x squared divided by x squared is 2. We still need our limit notation, so let's not forget that. The limit as x goes to infinity. 2x squared over x squared leaves us just 2. These cancel out. 10x over x squared leaves us 10 over x. X squared and x squared just becomes 1. 8x over x squared becomes 8 over x. And then the last one, 15 over x squared, nothing's going to cancel out. So this is what we're left with, and we can think of the limit of each part, okay? So what's the limit of 2 as x goes to infinity? It's just 2. What's the limit of 10 over x as x goes to infinity? The bigger that x gets, the smaller that value is going to get. It's going to get closer and closer to 0 because we're dividing a constant by x. The limit as x goes to infinity of 1 is just 1. 8 over x is the same thing as 10 over x. We're just going to get closer and closer to 0. And 15 over x squared is going to get to 0 even faster. So what's left here? 2 minus 0 is just 2. 1 minus 0 plus 0 is just 1. So our limit is 2. So what we can say is the limit as x goes to infinity of, we can call it f of x, equals 2. And what we call this, if you just want to know, is the dividing out technique. So if you hear someone say use the dividing out technique in another video or anything like that, that's what they mean. Divide by the highest power of x in the denominator. So try B on your own and then check your answer if you feel comfortable, ready to give it a try. Again, it's still x squared, so we're going to write that out, okay? I'm going to do it, but first you do it on your own and see what happens. Okay, hopefully you're coming back from having paused. I've got the limit as x goes to infinity. I've got x over x squared. What does that leave me? 1 over x plus 3 over x squared. So that's what's left on top. X squared over x squared left me with 1 plus 4 over x because 1x canceled out, plus 5 over x squared. So how is this going to work out? 1 over x is going to go to 0. 3 over x squared is going to go to 0 even faster, over 1 plus 0 plus 0. So what am I getting? 0 over 1, which means what? The limit as x goes to infinity of f of x equals 0. And another way you can say as x goes to infinity, y goes to 0. And you can see, looking at the graph, what's happening. It's going to closer and closer to 0, right? So that makes sense. That's good news. Trying again with C. Again, pause, try for yourself. If you didn't do B on your own, at least do C on your own. And then come back and see what happens. We're dividing by the highest power in the denominator, which is x. So I've got my limit as x goes to infinity. X squared divided by x would just leave me with x. Minus 4. 4x divided by x, the x's cancel out. Minus 3 over x over x divided by x is 1 minus 2 over x. So what happens here? This is our behavior for large values. As x gets higher and higher and higher, what's going to happen? Well, x is going to go where? We could just look at the x. As long as that x is on top, on the bottom, we're going to have 1 minus 0. So this is like, we could say x minus 4 minus 0 over 1 minus 0. Well, what happens if I'm going all the way to infinity? If I have like billions minus 4, the 4 is completely negligible. So what's happening? This x is going to keep getting bigger, and I am going to infinity. So as x goes to infinity, y also goes to infinity. That means the limit as x goes to infinity of f of x is infinity. Okay, so let's look at the next page. Okay, summarize and discuss characteristics and end behavior at horizontal asymptotes and slant asymptotes based on your observations in example number 6. So example number 6 was all of these graphs. What did we see here? Looking at A, we had a horizontal asymptote and a vertical. So what happened? The limit approached the horizontal asymptote. As x went to positive infinity, it approached 2. If we looked at the graph, we can see that as x approached negative infinity, it also approaches 2 on the y. So looking at B, what happened here? We were approaching 0. And then on the last one, we have this slant asymptote, we're approaching infinity, right? So let's come down to this page. Functions with horizontal asymptotes. The limit as x goes to infinity of f of x, it approaches b. We can just call it b. The limit as x approaches negative infinity of f of x, it's still approaching b. Let's just say that b is in the set of all real numbers, because that's necessary, okay? So y equals b is a horizontal asymptote of the graph of y equals f of x. Okay, so b is the horizontal asymptote, and the limit would approach b as x goes to infinity and x goes to negative infinity. Now, when there's a slant asymptote, we may recall, we looked at this earlier, that the limit as x goes to infinity could approach positive or negative infinity, and the limit as x goes to negative infinity can also approach positive or negative infinity. And we can give some options. We can use long division. I'm not sure if we even did that in a single one of our examples, but you may remember from pre-cal that you can use long division to find the equation of the slant asymptote. Okay, that is a method of how we can find the actual equation of the line that makes the slant asymptote. We can test values to find end behavior. That's what we did. Remember, we just kind of tested a value close to it and talked about would it be positive or negative. And then we used the divide technique. That was not supposed to say and, that was supposed to say find end behavior. So we're just listing here some options from what we did. And we can use dividing technique. Divide out technique. Sorry, that's a little messy. Hopefully you can read it. If not, go back and just hear me say it again. So the limit definition, the justification of a horizontal asymptote. If the limit as x goes to infinity, let me make this a little faster. Okay, there we go. If the limit as x goes to infinity of f of x equals b, or the limit as x goes to negative infinity of f of x equals b, then y equals b is a horizontal asymptote of y equals f of x. So this is what we've already seen and sort of talked about. It's just writing it out now as a statement of fact. And there is one more challenge problem here. Use algebraic techniques to find the limits for g of x equals 3x minus 3 over the square root of x squared plus 4, whose graph is shown. So we have a graph. We know what we should be getting as the answers. Try to use algebraic techniques and the information that we used here to solve this. I will tell you, for example, one sort of hint to get you started. If we wanted to divide by the highest power of x in the denominator, we would actually be looking at the square root of x squared, which we can say is the absolute value of x, right? Because no matter what x is, it's going to become positive because we squared it and square rooted it. So looking at that, try out the problem, and then I will work it out and you can watch it. But go ahead and pause first. This is me stalling to make sure that you paused. Okay, time's up. Here we go. So we already said that the square root of x squared equals the absolute value of x. Now you might be wondering, but what about the 4? Well, we do know that actually adding 4 to x squared isn't going to make a significant difference as we're approaching infinity, right? The larger the values of x get, the 4 doesn't become that important. But we can still work out this problem, right? So we have the limit as x goes to infinity of 3x minus 3 over the square root of x squared plus 4. And I'm going to do this by dividing by the highest in the power in the denominator. So I'm going to change it to the limit as x goes to infinity of 3x over the absolute value of x minus 3 over the absolute value of x all over. Now remember, in the bottom we're still in the square root, so it's just x squared over x squared plus 4 over x squared. And I can simplify this down, right? Because thinking about what's going to cancel out, this is going to go to 1. 4 over x squared is going to stay the same. This is going to go to 3. So I'm going to be left with the limit as x goes to infinity of 3 minus 3 over x, the absolute value of x, all over the square root of 1 plus 4 over x squared. So do the limits of those. The limit as x goes to infinity of 3 is just 3. 3 over x is going to go to 0, right? Because I'm going to keep dividing and it's going to keep getting smaller and smaller. Then I've got the square root of 1 plus 0, because 4 over x squared is going to go to 0. So I'm going to have 3 over square root of 1 is just 3, right? So I'm going to write out some little notes here. As x goes to a negative infinity, oh wait, I don't want to write that out. I was doing positive. As x goes to positive infinity, the limit is 3. That's what I need to write. Got ahead of myself. And this is g of x. So the limit as x goes to positive infinity is 3. That one is right here. Now let's look at the negative version, because we got to take both limits. X goes to negative infinity. The same thing's going to happen except one little trick. What's going to happen right here? If x is a negative, that's going to be a negative x divided by the positive x, right? Looking right here. If I have 3x over the absolute value of x, if that x was negative, 3 times the negative number is going to give me negative 3, and then I'm only dividing by the positive. So I'm going to have a negative 3 right here. Everything else is going to stay exactly the same. So what is that telling me? If everything else is staying exactly the same, then what's going to happen? I'm going to get negative 3 over 1, so it's just going to be negative 3. So we kind of took a shortcut there. And I just realized I sort of plugged in and canceled at the same time. This wouldn't be good for the AB exam. Let me fix it and give myself a little more room. Okay, what I did is I rewrote the actual problem, limit as x goes to negative infinity, and then I plugged it in, and we got negative 3. And so we see that the limit as x approaches negative infinity of g of x equals negative 3, which is over here. And that would be the end of that. So that's the end of the lesson, and you can go ahead and do the practice